Hello everyone, welcome back to my YouTube channel Study with This. Today we shall deal with data link layer, especially the introduction and block coding. In introduction, we would like to know about what are the types of error. So, whenever bits flow from one point to another due to the signal variations or interference in the signal, there might be a changes in the signal and hence the data as well. Hence, due to the interference, the shape of the signal will change and the error will be introduced. The two types of error are single bit error and burst error. The number of bits affected depends upon the data rate and the duration of noise. Usually, since the message length will be too much, always you can most of the time you can expect it to be a burst error itself than the single bit error. So here one's number of bits affected depends on data rate and duration of the noise. So here in the example I have taken 1 kbps and noise as 1/100th of second. This is the duration of the noise and this is the data rate 1 kilobits per second. So here 1 kilobits per second multiplied with the duration of the noise will give 10. So 10 chances of 10 bits being affected. So this will tell you how many number of bits will be affected. So here if the data rate is 1 kilobits per second and noise length is 100 second, then the number of bits affected is 10. Here in the figure you can see single bit error is out of all the whole message only one bit has been changed. So this is single bit error. If more than one bit has been changed, then it is called as burst error. Moving further, so once we know there is an error, how do we identify or detect the error and how do we correct error? To do error detection or correction, the central concept is redundancy. To detect or correct errors, we need to send some extra bits to our data. These redundant bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect or correct the corrupted bits. So, what is detection, error detection, and what is error correction? If it is error detection, we only look into basic thing is that whether the error is there or not. Simple yes and no will do the job. If there is error, yes. If there is no error, no. But whereas in correction, we have to know exact number of bits that are being corrupted and locations of that corrupted bits as well. So number of bits that is corrupted and location of these bits are also very important in error correction. Number of errors and the size of the messages are two important factors to locate the errors. For example, if one bit error is been induced in 8-bit message, then we need to consider 8 locations. So every location is being considered and we check whether the error has occurred or not. Likewise, if 2-bit error is being induced in 8-bit message, then we need to consider 28 locations, that is permutation of 8 by 2. 8 factorial divided by 8 minus 2 factorial into 8 2 factorial, it will give an answer of 28 locations. So we have to consider 28 locations and we have to check. So it is a tedious process once a millions of bits we are trying to transfer. Okay, what is coding? Redundancy is achieved through various coding schemes. The sender will add the redundant bits through the process that will create some kind of relationship between the redundant bits and the actual data bits. The receiver will check for the same relationship between these two, that is the actual bits and the redundant bits, to detect the errors. The ratio of the redundant bits to the data bits, this is one criteria, and the robustness of the process, the other criteria. These two factors are very important in coding scheme. And coding scheme has been broadly categorized into two things. One is block coding and one is convolution coding. Convolution coding has an too complex things like Galois field and all. So that's the reason we only concentrate more on block coding. Coming to block coding. In block coding, we are actually dividing the whole message into small blocks, each of k bits, and those are called as data words. So the small blocks message is divided into k bit small blocks and they are called as data word. We add r redundant bits to each block. So every k bit will be added with r redundant bits, and that block after adding the redundant bit is called as code word. So length of the code word, if it is denoted by n, then n is equals to k plus r, that is k bits of data word and r bits redundant bits. With k bits, we can create the combination of 2 to the power of k data words. Here I am not able to write it as 2 to the power of k, so I have written 2k. Kindly make a note of it. It is 2 to the power of k data words. With n bits, obviously we can create combination of 2 to the power of n code words. Again, here it should be 2 to the power of n and code words. Since n is again, because n is k plus r, so n is greater than k, the number of possible code words are more compared to possible data words. So there is list of valid code words and invalid code words. So block coding process one to one. So one data word will be in relationship with or in coordinated with another code word. So every data word will have one code word, and the remaining whatever is there which has not been mapped with a data word is will fall into invalid list of code words. So here the basic idea here is, in case the receiver receives any invalid code word, it indicates the data was corrupted during the transmission. So if it receives in the valid list, then obviously the data received was not corrupted and it is error free. If not, if it falls in the invalid code word list, then it was corrupted. Next is error detection. If two conditions are met, the receiver can detect the change in the original code word. That is, the receiver has a list of valid code words. Initially, to cross verify whether the received word belongs to the valid list or invalid list, he should be having the list of valid code words. And original code word has changed to an invalid one. This is also again important. Sometimes what happens, the original code word uh, might have been changed to an invalid one. So these two things you'll have to uh, make a note of it. So these two conditions you have to check. So here, what is the process of error detecting in block coding? If you see here, the data word of kbit is passed in the generator. It will add that relationship among the redundant bits and the data word. It will look into that process and it will add that redundant bit with the data word, and it will make the code word, and this has been transmitted to this receiver. Here, once the code word is been received, again that relationship is checked in the checker. Okay, if it matches and there is no problem, there is no syndrome, then only the k bit is extracted, that is the data word is extracted and it is passed. Otherwise, if there was a syndrome, then it is the whole thing is discarded, thinking that the data is corrupted. So that is what is here it has been said. A generator that applies the rules and procedures of encoding, and if the received code word is same as the one in which the valid code word is listed, if it belongs to that list of valid code words, then the word is accepted. If it does not belong to valid code words, if it belongs to invalid list, then it is discarded. And code word is corrupted during the transmission, but receiver word still matches the valid code word. It means the error is not detected. Even though there is an error, it is not detected. And error detecting code can detect only types of error for which it is designed, and other types of error may be not detected at all. So there are chances that there was an error, but we are not able to detect them. That are also possible. It is how it has been decided, and for what kinds of error it has been decided, it depends upon that. Example here, let's assume that the data word is of length 2 and redundant bit is only 1. So the code word length is 3, so n is 3, and data word is 2, so k is 2, and r is 1. This table shows the list of data words and code word. If you can see, 00 data word has code word 000. Likewise, 01 has 011. Likewise, the rest too also. Suppose assume the sender encodes the data word 01 as 011, okay, and send it to the receiver. So, what are the possibilities? The receiver has received 1 1. So, it simply means the sent was also 0 1, and it was supposed to receive 0 1 1 only, and it has received. So, it is a valid code word. So, the receiver will extract the data word from it and it passes. If the code word is corrupted during the transmission and instead of 0 1 1 1 1 1 is received, then the leftmost bit is corrupted. So, it is discarded. If the code word is corrupted during the transmission and 0 0 0 is received, that is, instead of 0 1 1 1 0 0 0 is received, then two bits are corrupted here, but still it belongs to the valid code word. So here the error remains undetected. You will not get to know there was an error. You presume it to be as data word 00 instead of 01. Next, what is Hamming distance? Hamming distance between two words is the number of differences between the corresponding bits. That is, any two words are given. If you apply an XOR operation between those two, and you will count for the number of ones in the result. If the number of ones is 2, then we say the minimum Hamming distance is 2. Likewise, the number of ones in that result will say the Hamming distance. So Hamming distance is found by XOR operation. Here in an example, if the code word is 5 zeros, it is sent and this is received, then 3-bit error has occurred. That is, XOR between 0000 and 01101 will again give the result 1101, or three ones in that. So obviously, Hamming distance between these two words is 3. If the D is non-zero, then the message is corrupted. The Hamming distance can easily be found if we apply XOR operation on two words and count the number of ones, as I said earlier. Again, another example is been given, applying the XOR operation between these two words. Okay, so 10 is 1, 01 is also 1, 11 is 0, again this is 1, and this is 0. Again, since the number of ones is 3 here, again 3 is the Hamming distance between these two words. What is minimum Hamming distance then? Minimum Hamming distance is the smallest Hamming distance between all possible pairs of code words. If our system can detect up to yes errors, it simply means that the minimum distance between two valid code words will be one more than the number of errors. So, for example, if 2 bits error it can identify, then yes should be 3, so that the received code word does not match the valid code word at all. So, if there was an error, it shouldn't be matching the valid code word. If minimum distance between, in the other words, if the minimum distance between all valid code word is s plus 1, the received code word will not be mistaken for another code word. The error will be detected at any cost. So this is the basic logic. To guarantee the detection up to s errors in all the cases, the minimum Hamming distance in the block code must be minimum s plus 1. That is, s error, suppose you want to identify two errors, then it should be 2 plus 1, that is 3. So minimum distance must be 3. The same thing is geometrically represented here. If you can see here, the dots within the circle and at the perimeter, then these are nothing but the errors. So anything out of this becomes the valid code word. So that is how it has been represented. So minimum Hamming distance for our first code scheme, that was in the table 10.1. If you can recall this table, if you see here, any two valid code word, if you take, the minimum distance is 2. Here also it is 2. If you check these two, again it is 2, likewise. So the minimum distance between any two code word in 10.2 is 2. in the table 10.1 is 2. So this code will guarantee the detection of only single error. That is, the 2 is nothing but s plus 1. So 1 plus 1. So it can only detect single bit error and not more than that. For example, if the third code word is 101 is sent and one error occurs, the received code word does not match any of the valid code word. If in case two errors occurs, however, received code word may match the valid code word and hence the error might remain undetected. This might happen. So we can't uh, identify more number of errors. That is minimum distance whatever is there plus one. After that, it means S errors you can identify, not more than that. Linear block codes. This is a code in which exclusive or two valid codes will create another valid code. Suppose in our previous example 000 and 011, if these are the two valid codes, the XOR operation between them will again produce another valid code word only. This is basic logic with the linear block codes. For an example, if you see here, the code, the same thing, same table they are trying to explain. 00 will font to 000, 012 011, 102 101, and 112 110. So same example they are trying to quote here. um, yeah, the linear block code will result, the whatever the linear block code is there in the table, uh, the XORing those any of the valid code word will again be the valid code word only. So XORing the code word in that table will again produce one more code word in that table itself. So this is the whole concept of linear block codes. What is minimum distance for linear block codes? It is simple to find the minimum distance. That is the number of ones that is present in the result of XORing two valid code words. So it should, minimum having distance is the number of ones in a non-zero valid code word with the smallest number of ones. For an example, in our first code, that in the table, the previous table what I showed, the number of ones in the non-zero code word are 222. So the minimum having distance is 2. As I said earlier, if you can just see here, if you XOR any of these any two code words, the minimum distance will be 2 only. So that is what they are trying to tell here. Then the last one today we'll be dealing is parity check code. Here this code is a linear block of code. A k-bit data word is changed to an n-bit code word where n is just one bit extra than k-bit data word. That one bit will give the parity, whether it is even parity or odd parity. For our comfort, we are going with even parity. So that extra bit is called as parity bit, and it is selected to make the total number of ones in the data word, in the code word as even. Suppose the data word already had even number of ones, then the parity bit you are adding will be 0. If the data bit had odd number of ones, then the parity bit will become 1, so that after parity bit has been added and it is made a code word, that code word will always have even number of ones. So this is the basic idea of parity check code. So here parity check code only can detect odd number of errors and not the even number of errors. There is one more table here with k is 4 and n is 5. You can see here, this is the data word. See here, number of ones is 0. So 0 means even only. So we are adding 0 here in the code word. If you can see that blue color here, this 0 has been added just because even number of ones. Here odd number of ones, that's the reason we are adding 1, and in total here it is even number of ones. Here also the same thing, odd number, so we are adding here and we are making it as even. But whereas here it is already even, and that's the reason we are making it as 0. Likewise all these are being made, so we are adding one redundant bit, that is a parity bit. How do we do that? How do we get to know whether to add 1 or 0? This is the diagram for that, wherein we are adding A3, A2, A1, A0. Okay, and modulus 2 will give either 0 or 1. If it gives 0, add 0. If it gives 1, add 1. It will only give what is the parity, it has to be added. The same thing, it is given to the generator and the parity bit is decided, and formula is nothing but this one. If you can see here, all these things divide modulo 2. So that will give the parity, even parity, and that can be added here, and this has a whole code word is sent here. Again the same process has been made here. The addition of all the 5 bits and modulo 2 is taken, so that here that is done by the checker, so that if there is a syndrome, if it is a non-zero number, except 0 if it is 1 or 2 anything, then it is a syndrome and the whole message has been packet has been discarded. If not, then that is if the syndrome is 0, then the redundant bit is removed and the rest is passed to the application or the higher layers. The same thing I have explained here, what happens when syndrome is 0 and syndrome is 1. The example here, one we have to look into. Suppose the data word is 1011, so it is odd number of 1. So at the we have to add parity bit as 1. So this becomes our code word. If you see, the same thing is been sent, no error at all. For an instance, A1 has been changed. That is, this is A1. This is A not A1, A2, A3. So this has been changed. If that is the case, if one single bit error that will happen here, then syndrome will be 1 only, because 1 is been changed and it will no more be even number of ones. So you can detect it is very easily. But one bit single error that will change to R naught is changed here. That is, the parity bit is changed. So the data remains uncorrupted, but the parity bit or the redundant bit is changed. Then also it will throw an error telling that there was an error, but it is not the error. But we don't have any means to detect the error, and that's the reason we consider. I mean, we don't use it. We discard it in this particular parity check. And for an instance, there was an error in R naught and second error in A3. Then even number error has been applied here. So once even number of errors have been induced, then obviously the received code word will identify the code word received as valid code word only and not invalid. Why? Because it is again meeting the basic criteria that number of ones should be even, it is meeting it. So we do not consider that as an error. And if there are 3 bits that is being changed as errors, then obviously any odd number of changes will result in odd parity, and that's the reason we can easily identify the error, and that can be made make a note of it. So yes, so odd number of syndrome will be 0 1 if odd number of errors are being induced, and that's the reason we can also find odd number of errors once we are using parity check. Hope it is clear. If any doubts, kindly let me know through comment section. Thanks for watching.